let us start some question. So in the previous class, we learned that for any closed surface, if it is Q, so the flux would be simply Q by epsilon, right? Let's say if it is Q, so and some Q charge is placed at the center. So what would be the flux? Yes, Aisha, what would be the flux? Yes, hello. Hello. Am I audible? Yeah, maybe my internet is not stable. Yeah, so what would be flux, Aisha? Q by epsilon, right. So let me ask you a question that if I want to calculate flux through, oh, we get it. Yeah, Mariam already left. So, okay. So she just came here to tell me that she will do it. Yeah, this is good. So at least she will come, right? Yeah, so calculate flux through one of the faces of a cube, right? So we have to calculate flux through, this is some charge Q, and let's say we have to calculate the flux through this surface, this one of the face of it, right? So what do we know, Aisha and Saad? What do we know? Yes, yes, Maria, we thought that you already went to that reunion.
Okay. No, sir, I by mistake left.
Yeah. Okay. So I was talking about this question that we have to calculate the flux through one of the faces of a cube. So we have these cube, right? We have this one cube, and we have to calculate flux through, let's say, this face. We can have this face only, this upper face, this bottom face, this front, this back. But we want to calculate the flux at one of the faces. Okay. What do we know, Saad? What do we know? The flux in this enclosed cube would be how much? Yes, sir. So the flux through all these faces would be how much? Sir. Yes. Flux through the cube would be how much? How much?
I don't know.
So cube is the closed surface, right? Cube is, this is not exactly a cube, let's say rectangle, but for this closed surface, how much is the electric flux? That we have discussed, right? For any closed surface, the flux is how much? Are you not revising, sir? You have to revise, otherwise you will forget, right? So whenever you have any closed loop, so in the closed loop, the flux would always be Q by epsilon. Understood, sir? So cube is a closed shape. right? Cube is a closed surface shape. So the flux through cube is will be how much? So yes, that would be q by epsilon naught, right, sir? Understood, sir?
Can you repeat again?
Yeah. So a cube, let's say that this is a cube. So this is a cube and some charge is placed at the center. So let's say that some charge is placed at the center of the cube, right? So this is, now this is open from the top. This is open from the top, but let's say I put some charge in the center and I close this cube, right? So this is a closed surface. This is a closed surface, right, sir? So the flux through the closed
Yes, sir.
surface is always q by epsilon, right? So flux through all these surface would be how much? Flux through all these surface would be how much? Q by epsilon. Is this clear, sir?
Yes, sir.
So flux through all these surfaces are q by epsilon, which means that flux through how many surfaces? So we have this one surface, this second surface, third, fourth, fifth, and sixth. So how many surfaces we have?
6.
Six surface. So you see that from six surface, we see that from six surfaces, the flux is q by epsilon, right? But we have to calculate the flux from only one surface. Understood, sir?
Yes, sir.
So from one surface or from one face, it would be how much? Q by 6 epsilon. Is that clear, everybody? Maria, Maisha, and Sar. Is that clear?
Yes, sir.
Yeah. So whenever we want to calculate the flux through any surface, so we have to consider the total enclosed flux. And if we can calculate the total enclosed flux, so that would be Q by epsilon naught, then we can calculate any surface. Okay. So this was one question, and let us do one more problem, which is exactly similar to this. So let's say we have a surface, right, whose dimension is A, and we want to calculate the flux at A by 2 distance, from this point. So the charge is placed at here. A by 2 distance from this surface. And we want to calculate the flux. We want to calculate the flux through this surface. Okay. So is this question clear to you guys? Yeah, we have a surface, right? We have a surface which is A by A, right? And we have put one charge at A by 2 distance above this surface. Okay. We have put a charge A by 2 distance from this surface. So let's say this is the surface. This is the surface, and we have put a charge A by 2 distance. Let's say this is A by 2 distance from this surface. Okay, this surface. And we want to calculate the flux through this surface. Understood?
Yes, sir.
Yeah. So how can we do that? What do we know about this flux? Yes. What do we know about this flux, guys? So as I have said you that this is similar question to this one. So take the analogy from there. Yeah, who's got the answer? Let me give you a hint. That we know that flux through a closed surface is always Q by epsilon naught. Flux through a closed surface is always Q by epsilon naught. Right. So can you guys tell me now what would be the answer? Hmm? Anybody got the answer? Got the idea?
Q by A by 2 epsilon naught.
Yeah, Q by how much epsilon naught? A by 2
Epsilon.
by 6 epsilon. Yeah, so the area, why is A by 2 coming? Right, because charge is so Q by 6 epsilon naught is the right answer. Why A by 2 is coming? Do we have, so Q by A would be, Q by A would be sigma, right? The flux is Q by epsilon, not Q by A. Electric field is sigma by epsilon, right? Flux is Q by epsilon. Why is A coming? Right, so we can do this problem by making it a closed surface. So let's say that this is the surface, right? In our case, this is the surface and we make it a closed. So how do I make the diagram? So my diagram is pretty bad. Let me make a few. So this is mm, and this is, so how do I make it? Okay. So please see this diagram. Please see this diagram. So this is a surface, right? This is a surface and a charge Q is placed A by 2 distance from it. So how many surface we will need to make it a closed surface? We have one surface, right? We have one surface and a charge is placed. A charge is placed A by 2 distance from this surface, right? So how many surface do we will need to make it a closed surface? Aisha, how many surface we will need to make it a closed surface? Yeah, 5. Did you say 5?
Yes, sir.
Yeah, so if we make a 5 surface, right? If we make a 5 surface, so this was one surface and we make one surface above, 2 surface beside, and in the left and right the other surface. So 5 surface we make and we make it a closed surface. So in the closed surface, the flux is in the closed surface. Let us assume that this is a cube. I don't know how to make a cube of this surface. So from the 6 surfaces again, this is Q by epsilon. So from one surface, it would be Q by 6 epsilon. Understood, guys? Sada, did you understand this part?
Yes.
Yeah, the idea is that we have to make a closed surface. 5. Yeah, Mariam, yeah, you are right. We need 5 sides to make it a closed surface. So if the idea is that whenever we can make a closed surface, then we can tell what would be the flux through one surface. Okay. So you guys please quickly note down these two problems, and then we will do one more problem. Okay. And then we will solve the other question. So you guys please quickly note down these two problems. Whenever you guys have done, so noting down, please. Just remember the idea that we need to make a complete closed surface. So, yeah. Done. Okay. So done.
No, sir.
Oh, please.
Yes, sir. Done.
Done. Okay. So let me give you guys one homework. Let's say that a charge is placed at this corner, right? At the edge of this corner. So then you guys calculate what would be the flux. So take it as you just uh, just remember that how can you make this charge enclosed, right? A charge is placed at the corner, at the edge of this corner. Okay, guys. So did you guys get the problem? So the question is that a charge is placed at here. Okay. So calculate flux. Understood? Yes, guys, understood.
Yes, sir.
Yeah, so you guys need to think that how can we make this charge in the closed surface. So if I place one cube here, one cube here, one cube here, so how many cubes would I need to make it a closed surface? So you guys think about that. And yeah, so this is your okay. And yeah, so one more question. You have a charge which is placed at the hemisphere. Right, this is placed in the hemisphere. So what would be the flux through it? What would be flux? How can I make this charge in the closed surface? So I have a charge in the hemispherical surface at the center. So how can I make this a closed surface? How can I make this a closed surface?
Here.
Yes,
By adding
by adding
Another hemisphere on top.
Yeah, by adding another hemisphere on top, right? So this makes it a close sphere surface. And if yes, so did you, Aisha, did you say the same thing?
Yes, sir.
Yeah. So if I place this on the top, so the flux in this region would be how much then?
Q by epsilon 0.
Q by epsilon 0, Q by epsilon naught. And this is two hemispheres, right? So two hemisphere gives Q by epsilon naught. So one hemisphere would give me Q by 2 epsilon. Understood, guys? Sad. Understood?
Yes, sir.
Yeah, please quickly note it down, and then we will do one more problem, and then I'll talk about this application of cluster. So this is also the application of Jasola. Yes, done, guys.
Done, sir.
Yeah. So remember that we have to always remember that for closed surface, phi is Q by epsilon. Right? Q enclosed, if I want to be more precise. So we have one more question, which is that we have this electric field, which is only in the x direction. So this is alpha x to the power 1. Okay. So this is only in the x direction, positive x direction. And we need to calculate the flux through this cube. Okay, so we need to calculate the flux. This is A distance. This is the A side of the cube, right? And the electric field direction is this. Right. So we know that, okay. Sana, the exam will start at 8:30, the classes also. Because we have only completed half an hour of class. So, Sana has not joined the room. Okay. Yeah. So this is the direction of the electric field, and a charge is placed here, and we want to calculate the flux through this surface. Okay. We want to calculate fluxes out. Right. Understood, guys?
Can you explain that EX part?
Yes. What do you say?
What did you write in that box?
Put it. Why did I put this
I
charge?
also had EX.
Ex.
Yes.
Yeah, so this electric field is only in the x direction. This is x, this is y, this is z. So this electric field is only in the x direction. Okay.
Yes.
And there is not any charge. So, okay, only this electric. Understood. So the flux would be how much? Total flux would be this in the closed surface, the total flux would be how many surfaces are there?
6.
6, right? So this is left surface. Let me write it as, so this is left, this is right, this is up, this is down, right? This is front, and this one is back. Understood, guys? Yes.
Yes, sir.
So the total flux in this closed surface would be phi L plus phi right plus phi bottom right plus phi up plus phi front and plus phi back. Any doubt in that? Yes,
No.
guys. And we know that flux is how much? Flux is E dot, right? Understood. So this is a dot product. Understood, guys?
Yes, sir.
So for the front case, so let's say that this is the direction of the electric field, right? This is the direction of the electric field, and for the front case, this is the front case. So for the front case, what is the direction of the area vector with this electric field? Yes. So this is the front face, and the direction of the area vector would be normal to this surface. Right, guys? Normal to this surface.
Yes, sir.
So, and my electric field direction is this. Okay, this is front. Electric field is this, right? So this is my electric field. My area vector direction is this. Let me put another page in that. So this is this. My area vector is this. So what is the direction between area vector and the electric field?
90 degrees.
90 degree. 90 degrees. So dot product and the angle between E and A is 90 degree for the front. So that would be how much? Cos 90 is 0, so this is 0. Understood?
Yes.
Similar case for the back. For the back case, this is so this is front, this is back. So for the back case, the area vector is this, electric field is this. Understood? So again, what is the angle? What is the angle? Chad, Bariya, Maisha, what is the angle?
90.
90 degrees.
90 degrees. So again, this would be 0. Right. And for the up case, this is up. Right. So this is the direction of the area vector. This is the direction of the electric field. So again, what is the angle between them?
90 degrees.
90 degrees. So again, how much? 0. And phi down. So again, this is down, area vector is this, and the electric field vector is this. So again 90. So this is again 0. So this cancels, this cancels, this cancels, this cancels. Only these two will survive. Right? Because for this case, for this phase, the area vector is this, and the electric field is also this. So the angle between them is 0 degree. Right, guys?
Yes, sir.
So for the right case, this is the right phase. Electric field is in this direction, and this area vector is this direction. So let us calculate phi r. Phi r would be E and A cos 0 d. So this would be simply EA. Understood, guys? Understood?
Yes,
Yeah.
sir.
And you guys know that EA varies as alpha x r. So what is the value of x at this point? What is the value of x at this point? What is the value? Yes, guys. So at for this phase, what is the, so this is A, this is A. So how much?
2A.
2A, yes, 2A. And area would be how much? For this, this is A, and this is A. Right, so area would be, understood, guys?
Yes, sir.
Yeah, so this would be A alpha root 2 and A half and A square. So this would be simply alpha root 2 A 5 pi. Understood? Saad, did you get this point?
Yes, sir.
Yeah. And what would be phi left? So Saad will tell. What would be phi left? What is the angle between the surface?
180.
180. Yes, correct. Correct. So this would be EA cos of 180. So this would be minus of EA, and E would be how much? So E varies as x to the power half. So what is the value of x here, Saad? Yes, what is the value of x here?
I don't know.
I think first think, Saad, right, and then tell whether you know or you don't know. So for this surface is placed at x equals to a distance. Right? Am I correct, sir?
Oh, sir, 2A, 2A.
No. This surface. We are calculating the left surface. So left
So,
surface is placed at x equals to a. Right?
yeah.
This right surface is placed at x equals to 2a. This right surface. This
So
left
2.
surface, yeah, 2a or a. Left
A,
one,
sir.
a.
The left
Yes.
one A, right one 2A.
Yeah. Now you are absolutely correct. So E would be alpha and X is a half, right? And A is how much? If this is a cube, so this surface
Area.
is A square, right? So A square. So this would be minus of A and A half A square. So this is A 5 by 2. So this would be the phi L. And total flux would be how much? Phi L plus phi R. So this would be alpha root 2 A 5 by 2 minus alpha A 5 by 2. So this would be alpha A 5 by 2 root 2 minus 1. Any doubt in this question, guys? Any doubt?
No, sir.
Yeah, so please quickly note down this problem. Please quickly note down this problem. Yeah, so the test has been made active, the class assessment test. Yeah, so Mariam, if you get the time, please take that test and yeah, and rest of you guys, Aisha and Saad, please take that test, which will happen after this class. Okay, guys.
Yes, sir.
So today's class will be only of 1 hour because I had to take some other class and yeah, we had to reschedule this class. And what I want is, guys, that I want to complete 3 chapters before the end of the July. So what I will do is that I will take some extra classes, maybe on Saturday. So can you guys come on that day, or can you guys take out some extra time for this class? Yes. Will that be possible, guys? Yeah,
It is fine.
yeah, okay. Okay. Yeah, for Aisha, it is fine. What about Saad and Maya?
Sir, Saturday
What?
is fine.
Okay. Saad, Saad, I'm saying that I want to complete 3 chapters before the end of the July. So to do that, as you can see that my pace is very slow, right? So to complete 3 chapters, I have to take some extra classes. So what I am thinking that, yeah. So what I am thinking that we can take some extra classes on Saturday. So will you be free? Yes.
Timing.
Timing, yeah. So timing, you guys will decide. But before 4 p.m. KSA, before 4 p.m. KSA, whenever you guys are free. After
Sir,
afternoon and yes.
on Saturday I have 2 classes. From 4 p.m. I have chemistry and 6:30 I have maths. So
Okay.
anytime between, yeah, 2 hours
Hmm.
before 4 p.m. you can.
Okay. Okay. Okay, Aisha. Now, so yeah, whenever if you're traveling, then yeah, from the next Saturday. Okay, from the not this Saturday, Aisha, in the next Saturday, if you're not available. Okay.
Sir,
So yes, Maya.
sir, can you scroll?
Oh, so oh, sorry about that. Yeah, because I want to be ahead of your speed. Right, because there will be exams that will happen just after this opening of the school, and yeah, so I want to complete those chapters before the school opens. So that is why I would be taking some extra classes. Okay, done, everybody.
No, sir.
One minute.
Okay. Thank you. Saad and Mariam, done.
One second.
Yeah, so just remember that for this case, there was an external electric field. There was not any charge enclosed, but there was an external field. So that is why we got this kind of electric flux. Okay, guys.
Done.
So I've done.
Yes, sir.
Yeah, so now let us understand about this, just quickly understand about this continuous charge distribution. So we have three kind of continuous charge distribution. One is this linear charge distribution. Right. So for the linear kind of charge distribution, we have this linear charge density, which is defined as Q by L. Okay, guys.
Yes,
Understood?
Sir, can you repeat again?
Yeah. So we have this continuous charge density, charge distribution. Let's say we have a line charge, right? And the charges are placed like this. So this is a linear charge distribution, right? So there is a thing called linear charge density, right? So linear charge density, as density refers to, so whenever I define mass density, right? So mass density is mass by volume. So this is called the volume mass density, right? Understood, sir? So mass density, yeah, mass density means mass in the numerator, and density means whether it is volumetric, surface, or linear. Understood?
Yes, sir.
So if I have a linear charge density, so the denominator will have L. And charge density means that charge will be in the numerator. Understood?
Yes, sir.
And let's say I have some charge which is distributed on the surface. Maybe this surface, maybe this surface. Right, so charges are distributed on the surface. So then we have a surface charge density. So this is a linear charge density. Okay, then we have this surface charge density, which is denoted by sigma, and this would be how much? Saab, you tell me. Remember, this is surface and charge density. So this would be how much? Just take the analogy from linear. So this is L, charge density. So this is Q by L. So what would be surface charge density? Yes.
Q by A.
Yes, absolutely right. So okay, I am arranging the class tests. Yeah. So Q by L, absolutely correct answer. Right. So Q by L. Understood. And yeah, so as you can see that this is density. So if I tell you about the uniform charge density, so this will remain same for the small charge and small area also, right? So if this density is uniform, so this density will be also the same as the total density. Understood?
Yes, sir.
sir.
Yeah. And then lastly, we have this volumetric charge density. So volumetric charge density is represented by rho, which is Q by. Understood, guys? So the example of this is this sphere. Right. So this will have some rho charge density. So this is the surface, hollow sphere. Okay. So on the hollow sphere, the charges are distributed at the surface. So there is no charges inside for the case of the hollow sphere. So the hollow sphere will have this surface charge density sigma. The solid sphere, right? This is a solid sphere. So this solid sphere contains the charge inside also. So this will have a volumetric charge density. Is that clear, guys? So you guys quickly move down this part. Yeah, whenever you guys note it down, please tell me, then I can start immediately. If this class would have been 1.5 hours, then I would have completed this chapter. But so the second chapter is also a big one. The third chapter is comparatively a small one.
Okay.
Done. Okay. So the next Saad and Mariam, done.
Yes, sir.
Okay. So the next topic is application of Gauss law. And from this Gauss law, we will calculate the electric field of infinite line charge, right? And then we will calculate the electric field due to sheet, and then we will calculate the electric field due to hollow sphere. Okay, guys. So only these three were done in your school, right? Yeah. Do you guys remember that only these three topics is done in your school? So we'll stick to that. Okay, only these three are in your syllabus. So okay, so the electric field due to linear or infinitely long wire. Okay. So we have this long wire, and this has some linear charge density. So what would be the electric field due to this long charge at this point? Let's say this is r distance at this point. Okay, understood, guys?
Yes, sir.
Yeah. So let me. Okay, guys. So we have some good news. I can take this class for 1 hour. So we have half an hour more, and we can complete this chapter. So can you guys be there for half an hour more? Or do you guys have some work? Mariam has some work. She has to go outside. So yeah, are you guys available for half an hour more?
I have another class on 6:30.
6:30. So 6:30 is 9, right? Okay. So okay. So what we can yeah. So we will end the class. Let's see. So can we have this 10 minutes more?
Yes, sir.
Yeah. So we need to calculate the electric field due to this infinitely long wire. So we have to apply. The idea is that we have to apply the Gauss law. Right. And what do we know about this Gauss law? We know that flux in the enclosed surface is how much? Q enclosed by epsilon. Right. This we know. So to apply Gauss law, we have to make any surface which is enclosing this charge. Understood, guys?
Yes, sir.
Yeah, so that's where this Gaussian surface comes into, so Gaussian surface. So what is a Gaussian surface? Right. So it is a geometrical concept to easily calculate the flux. Right. So we can choose any kind of Gaussian surface, but we have to follow two things. And what are those things? To apply the Gaussian surface, we need to have, so what is flux, guys? In the closed surface, what is flux?
Number of immediate.
Right. This is for the closed surface, right? So we choose, okay, sir, got disconnected, sir. Yeah. So we choose any kind of Gaussian surface whose surface and electric field are either perpendicular or parallel to each other. Right. So if they are perpendicular, so then this would be 0. And if they are parallel, so this would be phi would simply be how much? E ds. Right. So this is the first rule for the applying the Gaussian surface. Understood, guys?
Yes, sir.
And the second point is that this electric field is uniform. Electric field is uniform or constant. Right. So we can take this E outside of this integral, and we have to only integrate this ds. Is that clear, guys? It is
Yes, sir.
constant.
Yes.
So this is how we choose this Gaussian surface. Okay. So to apply this Gauss law, we choose a Gaussian surface, and it is a geometrical concept to easily calculate the flux. Okay, guys. So it has two conditions. One is that E and ds has to be perpendicular or parallel, and second is that electric field is uniform or constant. Understood? Yes, guys, understood.
Yes, sir.
Yes, sir.
Okay. So let's say that I have a point charge. I have a point charge. So what kind